Okay, we're now recording. Let's get the slideshow set up from the current slide and we'll be ready to go. I hope we'll be ready. Here we go. All right, before we get started on that, as I just said, next week, bad news all the way around. No classes at all. Sorry about that. But we have meetings Monday and Tuesday and a duty day Wednesday. So that means the college will be open Monday, Tuesday, and technically Wednesday, okay? However, sort of like this class today, this morning, only 2 people here. Wednesday afternoon, it's going to get pretty sparse around here. So if you have any business to do with the college, best to get it done Monday or Tuesday or Wednesday morning. There will be people in every office. I know those times. Sometime Wednesday afternoon, typically, it's never guaranteed, but typically they do allow people to go home early. And so the odds are Wednesday afternoon, you may find some offices completely vacant. So get your business done Monday, Tuesday, or Wednesday morning. Now, if you're looking for instructors, and actually many other people, we are going to be, if folks are not going to Montgomery where the state meetings are, then we're here for what they call local professional development, and they always have something that they want us to attend, generally on the Birmingham campus. So Monday and Tuesday, the odds are you'll find very few instructors here on this campus. So either be in Montgomery or in Birmingham. But offices will be open. Now, Wednesday is a local duty day, and a lot of people take that as a personal leave day. I haven't heard whether I'm taking it as a personal leave day or not. I'll have to check with the boss at home and see what she says, but there is a chance I might not be here, or might not be here the whole day anyway. I think we heard last night her brother's coming through town to go up to Huntsville to visit with his folks over Thanksgiving, and he's going to stop around noonish. But she wasn't sure whether they just stop at a restaurant somewhere or stop at the house. If they stop at the house, then she'll probably say, why don't you come home? Okay. If it's just at a restaurant, then I probably wouldn't be able to meet them there anyway. So I don't know if I'll be here Wednesday or not. I'm pretty sure I'll be here Wednesday morning, but I don't know how late. But anyway, that's next week. All right, let's get moving on 2.6. Any questions on anything we've done so far? And let me just say this, I know preaching to the choir almost here, but I want to remind everybody this is one of my better classes as far as getting papers in, okay? However, it's still way fewer than half the people have turned in papers. Thanksgiving week is your last best shot to get them done, because after that, it's going to get hectic. There's going to be projects and papers and finals and everything else happening. Please get working on your papers if you haven't already. Also, let me say this. The first quiz, there's 1, 2, 3 people haven't turned in the first quiz. All right. Goodness gracious, I can't see. I can't find, there you go. Okay. Okay, I was just saying, no classes next week, I guess you know. School will be open Monday, Tuesday, and at least Wednesday morning. Technically, it's open all day Wednesday, but a lot of people will be going home early, I think. They usually let people go early. So get your business done then. Secondly, papers, please, if you haven't gotten those done, work on those over the week that you have. Remember to turn it in November, you still get 1 bonus point. If it's into December, 0 bonus points. Okay. And number 3, I was just going over the quizzes. Quiz 1, what did I say? 1, 2, 3 people have, oh no, wait. 2 people haven't turned in quiz 1. One of those early ones withdrew. That means several haven't done or finished test 1. I'm not even going to count. It's fewer than half have finished test 1. Okay? Quiz 2, I just got my 3rd one in. And we're getting awfully close to test 2. So please get your stuff caught up over this Thanksgiving break while you've got some time to do so. Any questions? All right. We're continuing in polynomial and rational functions, and to me that's way out of focus. What do y'all think? Is it? Let me see if I can do anything to improve that there. Sometimes you have to check its memory, I guess. I don't know. Okay. Now, the first 5 sections have dealt with the polynomial functions. This section is starting on rational functions. Okay? What does rational functions mean? Of what kinds of functions? Polynomial functions, exactly. You have one polynomial function in the numerator, one in the denominator. Now remember, polynomial functions can be very simple, and as in single numbers, single terms, are fairly complicated. Okay? The first thing we're going to do is find the domains of these rational functions. What would you guess is going to hinder the domain besides Tyler coming in? Okay. No, I'm sorry. Okay. What would hinder or restrict the domain of a rational function? What is it? There's only 2 things we've talked about that limit domains. All right. Jessica, right? Okay. All right. 2 things that limit domains. 2 things you can't do in mathematics. Especially when you're talking about dividing. Second? Yes, you cannot divide by 0, ever. So what's going to restrict the domain of a rational function? The numerator won't matter any. Remember, polynomial functions are good everywhere. Okay? But the denominator, any places that denominator might be 0, out. You cannot have it there. Okay, we will then talk about finding vertical and horizontal asymptotes. By the way, I'll clue you in. Vertical asymptotes have to do with those zeros and denominators. Horizontal asymptotes, different issue though. We'll talk about those. We'll sketch graphs of rational functions. Once we know how to do this, we'll be able to sketch graphs. And Darlene is here. All right, good deal. Okay? We'll sketch graphs of rational functions that have slant asymptotes. No, we won't. Okay? We're going to skip that section, subsection. And we'll use rational functions to model and solve some real-life problems. Yeah, we'll do that. 1 or 2 anyway. All right. Introduction. Okay. A rational function, as you just stated, is a ratio, otherwise known as a quotient, of 2 polynomial functions. Okay? It can be written in the form of f of x, rational function here, is equal to n of x divided by d of x. Quite often in this book, when they capitalize a name of a function, that usually indicates it's a polynomial. So that's what we mean, but why would they name it n and d? Numerator and denominator. The numerator polynomial and the denominator polynomial. Where n of x and d of x are polynomials, as long as d of x is not the 0 polynomial. A 0 polynomial will just be 0, okay? The number 0. Can't have that. You can have d of x that has zeros in it, but that's going to give you limitations on your domain. Normally, polynomial functions have no limitations on domain, but because you got one in the denominator, it may. Not it itself, but the whole rational function. In general, the domain of a rational function of x includes all real numbers except for those x values that make that denominator 0. That's what we pay attention to first. Much of the discussion of rational functions will focus on their graphical behavior near those x values excluded from the domain. And you'll see it's a fairly common and consistent response there. Okay? So here's example 1. Pretty simple rational function. Okay? ratio of the polynomial function 1 to the polynomial function x. Okay? Really simple functions. It says find the domain of that polynomial rational function. Now, where do we usually begin? All real numbers, unless there's some value you have to exclude. Any values here you think you might have to exclude? X equals 0, because that makes your denominator 0, right? So x cannot equal 0. So find the domain of the function. One way to say it is, let me get my pen activated. Okay? X cannot equal 0. Now, that's pretty simple. Usually they'll express it this way. The domain of this function f, they may not use this terminology, would be the set of all x value, all real numbers x, such that x is not equal to 0. That's the way to express it in set notation. How about interval notation? You tell me. How would you express that concept in interval notation? Okay. Second? Okay, you start at negative infinity. That's always preceded by parentheses. Goes as far as 0. Does it include 0? How do we indicate that? No, bracket would include 0. Parentheses does not include 0. And then you union that with open parentheses, 0 to positive infinity. You got it. Okay, I can't write this morning, but that's it in interval notation. Okay, there's your doing. Discuss the behavior of f near any excluded values. What's your only excluded value? 0. So let's talk about what happens to the function f when x gets close to 0. Now, where do you want to start? Approaching 0 from the left, negative values, or approaching 0 from the right, positive values? You tell me. Positive, okay? Give me a value for x. Second, 2, okay? What is f of x? Second, f of x is 1 over 2, okay? 1/2. So give me another x closer to 0 than 2. 1, okay? What is f of x then? 1, okay? Whoops, okay, it's going up a little bit. Okay, give me another value closer to 0 than 1. Okay, and what's f of x? 1 over 1/2, which is 1 over 1/2. Okay, 1 over 1 over 2. How do you divide fractional forms? That's same as 1 divided by 1 over 2. How do you divide fractional forms? You change the division to a multiplication. We just did this, didn't we? 2 over 1. Okay, and what's that? Say again? 2. All right. Ooh, feel like a dentist here. Okay. So when x is 1/2, you're up here at 2. Give me another value closer to 0 than 1/2. 1/4. What would your f of x be then? 4. Give me one closer. 1/8. What would that f be? 8. Okay, give me one closer. 1/16. What would it be? 16. Okay, one closer. See what's happening? Where's x going? Where's f going? Yes. Never touches. Never touches what? Okay, we're getting close to something. X equals 0 would be what we call, or not equal 0, a vertical asymptote. The closer you get from x to 0, which it can't ever be, this is going to positive infinity. Closer and closer to positive infinity. The closer you get to x, if it's 1 over 1,000,000, what would that be? X is 1 over 1,000,000, you'd have 1,000,000. 1 over 4 billion, it'd be 4 billion, okay? Get closer and closer to 0, it's getting larger and larger and larger. let's come to it from the left, from negative sides. What would be your guess there? Any guesses right off the top? Huh? Going to positive infinity? It's going to negative infinity, exactly. Because if you choose a negative number, pick any negative number. -1. What would your F be? -1. So you see, you stay negative there, but the closer you get to 0, it's going to negative infinity. So there we've discussed the behavior of F at those excluded values. As x approaches 0 from the right, it's going to positive infinity. As it approaches 0 from the left, it's going to negative infinity. All right. We didn't write it down, but hopefully you follow it. Let's erase this and see how they do it. Because the denominator is 0 when x is equal to 0, the domain of F is all real numbers except x equals 0. Every other number you can calculate f of x, but x equals 0 you cannot. So it's excluded from the domain. These tables show what we were just looking at. They use different x values, but got the same way. To determine the behavior of f near the excluded value 0, they're starting with -1, which y'all did. Found out x was -1 there. Now, as you got closer and closer, -0.5 or -1/2, it would be -2. -1/10 would be -10. -100 would be -100. -1,000th would be -1,000. So the closer you get to 0, the closer that gets to negative infinity, but never, of course, infinity is not a number, so you never reach it. It just keeps getting larger and larger. Negative. But when you approach 0 from the right-hand side, let's start over here at 1. You already said that 1/1 is 1. 1/1/2 is 2. 1/110. We didn't say it, but it is 10. 1/100 is 100. 1/1000 is 1,000. So the closer you get to 0, closer you get. I mean, it's just heading greater and greater and greater without bound. That is what we call positive infinity. All right. Now, note that as x approaches 0 from the left, f of x decreases without bound. In contrast, as x approaches 0 from the right, it increases. F of x increases without bound. Okay. Here's the graph that shows this. Y'all started actually with 2, and you found out this is 1/2 there. If you'd have gone to 3, it would have been 1/3, 4, it would have been 1/4, 5, 1/5. So you see, the greater x gets, the closer the value gets to. Second, that's a horizontal asymptote. The x-axis becomes a horizontal asymptote, both to the right and to the left. Because the larger your x get, positive or negative, the closer the f of x gets to 0. Always from the negative side here, from the positive side there. But we were more interested in what's happening as x gets close to 0, which is the excluded value. Here it's going to positive infinity, there it's going to negative infinity. Okay. Now, I can't remember if they introduced the... Yes, they do. Let's see if they put it on the slide. Yes. Okay? Here's how they express what we just were seeing. Okay? As f of x, I like to start with the x. Start with x and calculate f of x. As x approaches 0 from the left-hand side. Now this is looking pretty familiar, isn't it? This is what we talked about within behavior of polynomial functions. As x approaches positive infinity, where is f going? As x approaches negative infinity, where is f going? Okay? Now we're talking about as f is approaching as x is approaching the vertical asymptote. Go out, shouldn't have said that. The excluded value, okay? As x approaches 0, but now we have to say from the left because it's different when it comes from the right. So as x approaches 0 from the left-hand side, from the minus side, then f of x is approaching negative infinity. As x is approaching 0 from the right-hand side, x is approaching positive infinity. So again, our setup is exactly the same, okay? Except now, rather than x going to infinities, x is going close to the excluded values, both from the left and from the right. And then you determine what f of x is doing. Okay? Now, that x equals 0, as you've already indicated, is a vertical asymptote, meaning the function approaches the y-axis both from the left and from the right and never reaches it, so it gets closer and closer and closer. No value is here. Now, when the book, when it's the y-axis, doesn't put anything there. When it's some other number, they'll put a dotted red line. I usually dot the red line on the axis as well, and to me I use red because it's stop, don't go there, okay? Because the function is not allowed to go to x equals 0. No value is able to be assigned there. So that's called the vertical asymptote because the function gets close to it vertically but never reaches it. Make sense? Now, as you've already indicated, you also notice that the function is approaching the x-axis as x going to positive infinity, also approaching, and that's y equals 0, by the way, is the x-axis, as x approaches negative infinity. So you do have a horizontal asymptote as well. The function will never reach y equals 0, but it will come close. Now, let me say this about that. There will be some times when this function will cross a horizontal asymptote. It will never touch a vertical asymptote, but it can cross a horizontal asymptote, but in the long run, it's going to get closer and closer to it, okay? So you can have a value y is equal to 0. It's not disallowed, but that's where the function's going for greater and greater positive x values and negative x values, which sounds like in behavior, exactly what we did with polynomial functions. What happens to the function when x gets very large negatively or very large positively? Where's the function going? With polynomials, they were always going to an infinity. But with rational functions, they may go to an infinity or they may approach a fixed value. Okay? And usually it's going to be the same value, positive or negative. Okay? So we're going to determine what that is a little later. But there's your horizontal vertical asymptote at x equals 0, horizontal asymptote at y is equal to 0. And by the way, they don't always have to be the axes. A lot of times they will not be the axis. Just this one is such a simple function, that's where it's going. F of x 1 over x. Any questions on that? All right, I think I forgot to mark Jared here. Has anyone else come in? I didn't acknowledge you and put you on the roll. Okay. All right. From this figure, okay, I guess it's that figure, figure 221. From that figure, you can see that the graph also has a horizontal asymptote, the line y is equal to 0. By the way, that's how we name asymptotes. A vertical line is always x equals something, and a horizontal line is always y is equal to some fixed value. They're not always 0. The behavior of f near y is equal to 0 is denoted as follows. And this is exactly like we did it in the polynomial case, except I like to put the x in front. As x approaches negative infinity, f is going to 0. And you don't need to say plus or minus. This one happens to be approaching from the bottom, but you don't need to put that, okay? And as x is approaching positive infinity, f of x is also approaching 0. This time it happens to be from the top, but you don't need to say that, okay? Just it's approaching 0. So this is just like our setup for in behavior. It is in behavior when x is going to positive, negative infinity, okay? The difference is the f is not always going to positive or negative infinity. It may be, but it may not be, like in this case, they could be going to 0. Okay? Does that make sense? So you have your same setup. Be prepared to answer those kinds of questions. So here's the definitions of your vertical and horizontal asymptotes. The line x equal a, it doesn't have to be 0. The line x equal a is a vertical asymptote of the graph when f of x approaches either positive infinity or negative infinity as x approaches a from either the left or the right. Okay? As x approaches a either from the left or from the right. So basically you're going to have two setups here. You're going to say as x approaches a from the plus, so any order you want to, or x approaches a from the left, what is f doing from, and they're always going to be an infinity there for f of x near a vertical asymptote. Now, the horizontal asymptote, the line y equals b is a horizontal asymptote of the graph when f approaches b as x approaches either positive infinity or negative infinity. So if you have a horizontal asymptote, it's going to be as x approaches negative infinity, y is going f of x or y is going to b, and as x approaches positive infinity, y or f of x is approaching b. Okay? But it doesn't have to. If it's not got an asymptote, horizontal asymptote, it could be going positive or negative infinity. Okay? So you could have that as a case as well. Okay, Jajarian is preaching somewhere today. That's good to see. Okay, good deal. All right. Eventually, as x goes either the positive or negative infinity, the distance between the horizontal asymptote and the points on the graph must be approaching zero. Now, I said this, you won't run into many of these. That could be like this. It could be, oh, I'm sorry. Let's see. Okay, I don't like the way they worded that. Eventually, as x approaches positive or negative infinity, the distance between the asymptote and the points on the graph must approach zero. It's not approaching zero, it's approaching b, but the distance from. So even if they're oscillating, they're getting closer and closer to the further out you go in either direction. Most of the time, they're going to be smooth. They'll either be approaching from the upper side or approaching from the lower side in either direction. And you don't have to indicate it. All you have to say is it's going to be. But getting closer and closer and closer. Okay. This figure shows the vertical and horizontal asymptotes of graphs of three rational functions. Now, they don't tell you how they got them. Actually, I will tell you, okay? But for now, let's just look at the graphs. Okay? How would you describe this behavior out here? Tell me what you would say. Describe this end of the graph. As x is approaching negative infinity, what's the rest of it? F of x is, where's f of x going? Closer and closer to 2. It's approaching 2. Okay? How about this? Where's x going here? X. It's going to negative 1. As x approaches negative 1, from the left. This time you do have to put that little minus sign there. As x approaches negative 1 from the left, so from the minus side, okay, where's f going? Positive infinity. Okay, that's how you say it. As x approaches where? Negative 1 from the positive side. It's approaching negative 1, but from the positive side. Where is it going? Where's f going? Negative infinity. As x is approaching, where's it going? Positive infinity. What's the f doing? Say again? Going closer to 2. F of x is approaching 2. Now, you might ask yourself, where did those asymptotes come from? And really, they're pretty easy. The book isn't there yet, but I'll go on and tell you. First, vertical asymptotes. Where do they exist? Where it's the x value where the function can never go. That's why it's in red, not in red line. Can't touch it. Can't go there. Okay? Now, what determines where the function can never go? That is the value of x where the function does not have any validity. Why? Because the values are excluded. So what do we call that? It's where your domain is not defined. You cannot have an x value there. That's what your vertical asymptote is. What is it that prevents you from having a value defined there in a rational function? The only thing that restricts your domain in a rational function is what? The denominator can't be 0. Okay, so we look here at this function, f of x is 2x plus 1 over x plus 1. Ratio of two polynomial functions is a rational function. Where is that function not defined? Okay. Let me show you how I do it. What you just told me was your denominator cannot equal 0. What is your denominator? X plus 1. And what did you tell me it cannot equal 0? Okay? Solve that inequality. Subtract 1 from both sides, and that gives you x cannot equal negative 1. There's your vertical asymptote. X equal negative 1 because it can't go there. It can't touch it. So that's how you determine your vertical asymptote. Find the denominator, set it equal to 0, see what values it cannot have. If that was a quadratic, it could have 2 places it can't be 0. Then you have 2 vertical asymptotes. If it's a cubic, it could have 3. You know, that's why we need to know the zeros of the function, right? We need to know the zeros of that denominator. Every one of those is going to be a vertical asymptote. Now, what determined our end behavior with a polynomial function? Where did we look to determine what's happening at our end behavior of the polynomial function? It was called this type of test. Leading term test. Now they called it leading coefficient, okay? I called it leading term. What is it that's special about the leading term of a polynomial? It's the term with the, if you look at a polynomial, how do you know what the leading term is? Tell me. No, polynomial. How do you tell which is the leading term? You're just looking at that polynomial strung out there. Which is the leading term? It has a bunch of terms in it. How do you determine the leading term? The one with the largest exponent, of course. Okay? So, what we do, we usually write our polynomials in descending order of the power. That makes the leading term the first term, the one with the largest exponent, right? Now, that's how you determine, that's what you look at to determine the end behavior. If that leading term has an odd exponent, you know it's going either like this, right? If it has an even exponent, you know it's going either like this or like that, right? Okay? That's what you look at, leading term. So, for a rational function, what I look at is the ratio of the leading terms. You've got them in descending orders of the power. Look at the ratio of those leading terms. Okay? What is the ratio of 2x over x? Ratio of that. Simplify it. 2x over x. 2, exactly. And its y is equal to 2 because f of x stands for y, right? Right? So y is equal to, there's your horizontal asymptote. Right there, horizontal asymptote is y is equal to 2. That's how you determine the horizontal asymptote. Okay? Now, let's go to the second function. Okay. What would you look for first here? You choose, I don't care. Got 2 asymptotes, which one are they? Well, 2 types of asymptotes. Vertical and horizontal, which you want to look for first? Horizontal, okay. So what do you do to determine your horizontal asymptote? That's in behavior. Look at the ratio of your leading terms. What's that ratio? It's x, and remember, this is in behavior. X is very, very large. See, on this one, it doesn't matter whether x is getting large or not. The ratio is always 2. But here, if the x is getting very, very large, what does that ratio become? Give me a big number. Second?
642.
Small, 600. Let's just use 600. Make it easy. Okay? What is 600 squared? Maybe it's not that. Huh? It's squared, not double.
36.
Okay.
36 is somewhere.
36. Okay. You have 4 zeros. So 3, 6, and 4, 6. Yes. 360,000. Okay? Now what does that seem to be going to? Positive infinity. Okay? So this does not have a horizontal asymptote. That ratio is infinity. Okay? No, I'm sorry. 4 over 360,000. What is that close to? 4 over 360,000. Okay, that's 1 over 120,000. Very good, or whatever. But what's that getting close to? Can you draw it? Where would you draw 1 over 120,000? 1 over that? Okay, let's take 1/2. It is close to 0. It's getting awfully close to 0. So therefore, your horizontal asymptote is 0. Anytime when you do this ratio, you have your variable in the denominator, and it's getting large, and the numerator is a fixed number, that's going close to 0. And sure enough, the horizontal asymptote, I wish I had drawn the dotted line over the x-axis, that is your y equals 0, horizontal asymptote, so this is y. Okay, you did the horizontal asymptote. How about vertical asymptote? What determines it? That's right. Not when x equals 1. It's when the denominator equals 0. Then the denominator can equal 0, right? So we're going to do that one. Okay? So x squared plus 1 cannot equal 0. Can you solve that? No, you can't. Why? Yes, you get into imaginary numbers. The other way of looking at that, x squared at the very least is 0, right? You can't get any smaller than 0 for x squared because any number you square is going to be positive, except 0 is going to be 0. So it's going to, this is always a non-negative number. Add 1 to it, and it's always going to be positive. Always. So that will never equal 0, ever. So therefore, you have no vertical asymptote. This is defined in all real numbers. Okay? But you do have a horizontal asymptote, and because 4 is positive, and the denominator is always positive, this is always going to be positive. And that's what you got. Horizontal asymptote, the function is going to 0, y is equal to 0. Vertical asymptote, there is none. Okay. How about this one? Okay? What you want to deal with first? Vertical asymptote. Okay? What? And how do you determine vertical asymptote? Okay, denominator cannot equal 0. Okay, so let's write that down. X minus 1 squared cannot equal 0. Now, how can you determine what values you have to exclude? That's all you're interested in. Okay? So, x minus 1 times x minus 1 cannot equal to 0. Now, what would make that equal to 0? Cannot equal 0. What would make it equal 0? Say again? Okay, so then let's do it. X minus 1 cannot equal 0. And since they're not equal, and not or, x minus 1 cannot equal 0. Okay, is that what you wanted me to do? Is that what you meant? Maybe not. Oh, no, okay, okay. You could do that if you want to do more work and make it more complicated to see. This hopefully is pretty easy to see. What does this tell you? Second? 1. X cannot equal 1. On either case, X cannot equal 1. You add 1 to both sides, right? So guess what that is? A vertical asymptote. And sure enough, here it is. And X equal 1 is your vertical asymptote because you know it cannot equal 1. So never going to go there. Okay? Second?
So you don't have two vertical asymptotes.
You don't. Well, actually, it's a double vertical asymptote in the same place. Okay, so yeah, same thing. You don't have but one. Okay. Now that you found the vertical asymptote, what you want to go for next? Horizontal asymptote. Now, in this case, you could, if you wanted to, multiply that out. You know, either here or here, either way. But what would you have as your leading term for this thing in the denominator? Leading term. If you multiply that out, like you were suggesting, x squared, exactly. What's your leading term in the numerator? 2. It's the only term. What's the ratio of 2 over x squared? Always positive, but it's going to. X is going to infinity. You're talking about in behavior. And 1 over or 2 over infinity is going to be going to, just like we did before. Give me a big number, not 612, but 600. Square it. 360,000. 2 over that would be 100. 1 over 180,000. What's that close to? 0. Yes. So your vertical asymptote is the ratio of 2 over x squared, which because x squared is going very large, the ratio is going close to 0. So y equals 0 is a horizontal asymptote. I would put a dotted line in there. Now, what you have to determine here, and I should have done this on each one, is we should have set up our situation. In fact, let's go on and do that. Okay? All right, to erase this? Okay. Now, here are the types of things that you have to identify. Wait, I don't need that. Okay. As x is approaching something, f of x is approaching something. Okay? And we do that here. We do it again and again. Oh, and then the next time, yeah, we do it again and again. Okay. Ooh. Okay, I'm running out of room on that side. We have various things we want to look at. What are some of the things in this first one right here that you want x to approach? You have 4 things to choose from. Give me one of them. Especially as it pertains to asymptotes. Second? You may have said it. I couldn't hear. Okay, as x approaches -1, from which side? From the left side, so from the negative side. Where is your f going? Positive infinity, right there. As x is approaching -1 from the left, it's going up. Okay, next, give me another x approach. Anybody? Say again? Okay, another place the x is approaching one of those asymptotes. You did it from the left. Okay, no, that's, okay, no. All right. I want what x is doing. How x is responding to this asymptote, that's when x is going to negative infinity. When it approaches the vertical asymptote, x is going to -1 from the left. When it approaches the vertical asymptote from the other direction, -1 to the right. And then finally, when x is going to positive infinity. There are your 4 x approaches that we want. I don't care which order you do them, which you want next. Second? Okay, as x is going to positive infinity, where's your f of x going? Say again? 2, exactly. That's where F is going. Give me another place X could be going. -1 from the positive side. Very good. Where is your F going then? -infinity. Exactly. All right. And then let's give me one more. X is approaching -infinity. Is that what you said? Okay. -infinity. And where is the F going then? Approaching 2. Very good. You see how that works? There are the things. That lets you know you've identified the vertical asymptotes. Now you have 2 asymptotes, vertical and horizontal. Now you figure out what the X is doing as it's getting close, as it's interacting with both of those asymptotes in both directions. Okay? So that's good for that. Let me erase these because they're in the way. Any questions on that before I do? All right. Now on this one, on the second one, on the B one, we have as X is approaching something, F is approaching something, okay? But you only have one asymptote, horizontal asymptote, right? So X is only going in 2 directions there. So what are those 2 directions? Where's X heading? Positive infinity or negative infinity, just like it was in a polynomial function. Positive infinity, negative infinity. Where's your F going in both cases? To 0. Perfect. You see what it's telling you? The graph is showing you that. Do you see it? All right. All right. Need that up any longer? Are you okay? Okay, let's go to the third one. And again, you've got 2 asymptotes. They only show one because the other is the x-axis. So we'll have as X is approaching something, F of X is approaching something, and then you'll have another something, another something, another something, another something, another something, another something. Okay. So where is X going with regard to your 2 asymptotes? You pick any one of the 4 you want it to go to. Okay. From 1 on the positive side. As X approaches 1 from the as X approaches 1 from the right. Okay. From the right hand side. What is F doing? Positive infinity. Okay. Where else is X going? 1 from the negative side. Where's F of X going? Positive infinity there too. Next. X is going to negative infinity. Where is the F going? To 0. And as X approaches positive infinity, where is F going? 0 again. Good deal. You got them all. Make sense? All right. Good deal. That's a little beyond what the book's graph showed, but it shows it all. Okay? So let's go to the next. The graphs of f of x equal 1 over x here, and 2x plus 1 over x plus 1, both of these are called hyperbole. Okay, they call them hyperbolas. Okay, that's a Greek word, so it should be E, but never. Okay, this is hyperbole. Okay, and that's together that's a hyperbole. Okay, if you did this one, that's a hyperbole. Okay, they're mirror images of each other across that intersection of the thing. So those are hyperbole. Okay, you might look at that and say that looks kind of like a parabola, but it's not. Parabolas don't spread out; they keep going down. They go to positive or negative infinity in that case. So that's not a parabola. That doesn't have a shape. The next one over there looks like half a hyperbola on one side and another hyperbola on the other side. So we don't have a name for that one either. Okay, but these two, when they're going in opposite directions, mirror images across, not necessarily, this is the origin, but the intersection of the two asymptotes, those are hyperbole. All right, so let's talk about this. Vertical and horizontal asymptotes of a rational function. Here they have the generic rational function of all time. Okay, f of x is some numerator polynomial of x divided by some denominator polynomial of x. And you spell out this whole polynomial here. This is a degree m, that's degree n. Okay? N of x and d of x have no common factors. Now you have to take care of that first. So guess what you do to those rational functions? What's your F word? You factor them. Factor both of them as far as you can factor, okay? If you find any common factors, take those out. So that the numerator and denominator have no common factors. Now, the graph of F has vertical asymptotes for all the zeros in that denominator. So remember what we did with polynomial functions to find the zeros? You do the rational zeros test. You do Descartes' rule of signs. You use your upper bound, lower bound. You use synthetic division. You do everything in the book to find all the zeros of that denominator. What are they going to form? Vertical asymptotes. You may have one here, one here, one here. However many zeros you have in that denominator, each one of them is a vertical asymptote. Okay? Now, that's what you do for that. Now, the fun comes later. If you have a whole bunch of them, you have to say, what happens to f when x approaches this one from the left, that one from the right, this one from the left, this one from the right? You know, every one of them you have to let x approach that vertical asymptote from both the left and the right and identify where it's heading. Okay, done. That's your vertical asymptotes. Now, how about the horizontal asymptotes? It may have one. If it has a horizontal asymptote, it can only have one. Okay? It may have no horizontal asymptote. So here are the conditions. Now I'm going to do the same thing they do here, but here's what I suggest you do. Look at the ratio of the leading terms. Don't worry about the rest of them, just the ratio of the leading terms. That's going to tell you your horizontal asymptote if you have one. Okay, and here's the clue. If this n is greater than that m in that leading term, then that's not going to have a vertical asymptote because that's going to act like a function that has a exponent x to the n minus m. Some positive number, it's going to act just like a polynomial. So then as x goes to positive infinity, it's either going to positive or negative infinity. As x goes to negative infinity, it's either going to positive or negative infinity. It's going to act just like the polynomial with just those two, that ratio. If n is greater than m, you do not have any horizontal asymptotes. It's going to infinity in both directions. Maybe different infinities, but it's going to infinity. Okay. So let's imagine what if the n was equal to m? Well, then these cancel out, and guess what your ratio is? If n is equal to m, those divide out, and what's your ratio? The ratio of your leading coefficients. That could be 7 over 3, it could be negative 4 over 2, it could be any ratio. If these two exponents have the same power, same degree, that means that leading term, the x's cancel out, and you're just left with a ratio of a number. That's your horizontal asymptote. Plus, minus, wherever. That's your horizontal asymptote. All right. The third case, and that's this one here, when x n equal m, in other words, they have the same power, same degree, then the graph of x has a line y equal leading coefficient over leading coefficient, ratio of the leading coefficients. That's your horizontal asymptote. The third situation, what if the m is greater than n? In other words, n is less than m. Then, when you do the ratio, you're going to wind up with a number up here, and you're going to wind up with a variable down here. And as that x goes to positive infinity, that one's going to 0. As it goes to negative infinity, it's going to 0. So guess what? The horizontal asymptote when n is less than m is going to y is equal to 0. That's your horizontal asymptote, x-axis. That's it. Okay? So basically, look at the ratio of the leading terms. That will tell you the horizontal asymptote. Maybe one of three things. None, and y is equal to 0, or y is equal to the ratio of the leading coefficients. That's it. Okay? Pretty simple for all that big writing. Okay? So let's actually do something. I can tell y'all are excited. Okay? Y'all, yay! Okay. Right. Okay. Find all vertical and horizontal asymptotes of the graphs of each of those functions. That's all they're asking for. Which one you want to go for first on A? They're looking for vertical and horizontal asymptotes. Huh? Vertical. How do you find the vertical asymptote of A? What determines the vertical asymptote? Denominator, say again, cannot equal 0. What is your denominator? X squared minus 1 cannot equal 0. How would you proceed to find what values that might be? Say again? You could do that. Be careful though. And what does that give you? X squared cannot equal 1. Is that what you meant? Where do you go from there? It's already squared. Square root of both sides. What would that give you? X cannot equal, say again? I can't hear you. Okay. I told you to be careful. What did you say? And what is square root of 1? I told you to be careful, didn't I? You weren't careful. Plus or minus 1. Okay. If you were careful and put plus or minus, that gives it to you. Okay? Now, if you weren't careful, like somebody looked like they weren't going to be careful, the other way you could have done this would have prevented all that. Okay? And this is what I recommend, but if you like it that other way, as long as you're careful, you're all right. But what do we usually do to a situation like that? What's your F word? Factor X plus 1 times X minus 1 cannot equal 0. What does that give you? Say, yeah, exactly. X plus 1 cannot equal 0. And, not or, X minus 1 cannot equal 0. And this gives you X cannot equal negative 1, X cannot equal positive 1. That way you're guaranteed almost Sailor proof to make it. You find them both. And you take a square root and forget to do plus or minus, you're going to miss one. So this one has two vertical asymptotes, one x equal negative 1, one's equal x equal positive 1. That's your vertical asymptotes. Okay? I call these VAs. How about horizontal asymptote? Say again? Okay, we look at the leading ratio of the leading terms. And what is that? Not necessary. Say again? It's 2 because x squared over x squared is 1. Oh, yeah, okay. So, your vertical asymptote, how do you express that? Horizontal asymptote is? How do you express it? What is f of x? From the first of the term, what's f of x? Oh man, that was a long weekend, wasn't it? What's from the beginning of term? What's f of x? Always. Y. So this is y is equal to, you said it, 2. There's your horizontal asymptote. Your vertical asymptotes are x not equal to 1 and x not equal to negative 1. Your horizontal asymptote, this is your HA. Okay? Y is equal to 2. That's all they're looking for. We could draw the graphs if you wanted to, Right now they're just saying fine. All right. What might you do with B? Anything? If you're looking for horizontal and vertical asymptotes, what might you do? Okay, very good. Already picked that out. The ratio of the leading coefficients, leading terms is 1. So how do we express that? Y is equal to 1. There's your horizontal asymptote. Ding, 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 ding. Good. Okay, what do we need to do now? Second. So the thing you asked for. How do you get the vertical asymptote? Okay, very good. Except the first little phrase back in our box there was what? Where n of x and d of x have first one above 1 after your function. No common factors. Now, I told you when I said that, we factor everything in sight. So don't just factor the denominator. Good idea too, but you better factor the numerator as well to make sure you don't have common factors. Okay? So I'm going to clear that just a moment here so we can do it. Okay? Does that numerator factor? Say again? Does the numerator factor? Anybody? If it did factor, what would be the first things you'd write down? X times x. Where do you look next? Sign of the last term is negative, so these two have to be, say again, different. So one positive, one negative, okay? What's the only possible factorization of 2? 1 and 2? Let's try that and see if it works. No, it doesn't. Okay? What's wrong with it? Huh? Well, let's see. X times x is x squared. That's okay. And then you have minus 2x plus x is negative x. Not the number wrong. It's the sign wrong. So therefore, change the signs. Okay? That's my little rule. The book doesn't. Say again? Say that again. Okay, yeah. Oh, you could have swapped the other two and not changed signs. Yeah. That's more erasing. Never mind. I'm just kidding. It doesn't matter. Both of them would have been fine. Does that work? Yes, it does. Okay? Now we do the denominator. We could have done the denominator first. That's fine. What does it? Does it factor? Boy, he's not liking to factor anything today, huh? X times x. So plus and minus. Second. Second. 2 and what? 2 and 3. In that order? Let's see. X times x, sure enough, is x squared. That's all right. That will be minus 3x plus 2x. That gives you minus x minus 6. Yes, that works. And then what do you notice? Say again? Yes, they're both factored, but what more? They have a common factor, x plus 2. So you can eliminate the common factor. Now, here's a little trick though. You also have to remember, because it's down here, x cannot equal negative 2. That doesn't mean it's a vertical asymptote. Okay? You just have to remember x can't be negative 2. I'll show you why in a second. Okay? But now, you see, you still have your ratio of leading terms is now x over x, not x squared over x squared. but I knew it was going to come out the same, okay, then that's still 1. So your horizontal asymptote is still y is equal to 1. But now what's your vertical asymptote? The x equal minus 2 is not a vertical asymptote. Still can't equal that, but it's not a vertical asymptote. What is your vertical asymptote? Positive 3. X cannot equal 3 is your vertical asymptote. This is just something to note. It's not a vertical asymptote. Now, I'm going to graph that one for you, or at least set it up. Okay? Now, we know that you like dark red or bright red. You like red. You choose. Dark or light? Dark, okay? We know that y is equal to 1 is a horizontal asymptote. And we know x can't be 3. That's a vertical asymptote. Okay? Now, this is jumping a little bit ahead, but it's not too hard to do. Pick something on either side of that vertical asymptote. Well, actually, x equals 0 is real easy, right? That's going to be a number we're interested in, okay? At x equals 0, what is your ratio? When x is 0, those go away, and you have positive 1/3, right? Or when you do these two x's go away, then you have positive 1/3. So when x equals 0, you're at plus 1/3. Okay, that alone is enough to tell you where you put the lower part of this hyperbola. Okay? It has to go down in this sector here defined by those two asymptotes. But since we also know the numerator has x equal 1 has to be a 0, that's also a number on it. 1/3 here, 0 there. Okay? That tells me this function, I'm going to go back, I shouldn't have been in red now. That should have only been my asymptotes. That means this part is down here. Now, what we don't know is what's going to happen on the other side. So let's pick x equal 4. No, yeah, 4. And let's see where we are. This is a test point right there. That test point, x equal 4. Well, let's go to our simple form here. Our numerator would be x equal 4. What would the numerator be? Can you do that? X equal 4. What would your numerator be? It's not that hard. 4 minus 1. 3. What would your denominator be? X equal 4. X equal 4. 4 minus 3? 1. Goodness gracious. Okay. So when x is equal to 4, y is equal to 3. So when your x is 4, your y is, that was a 1, 2, 3. It's up here. That's all you need. Since you know the point is there, it's got to be approaching the vertical asymptote in that direction, horizontal asymptote in that direction. There's your hyperbola. Okay? With one exception. X cannot equal -2. So over here at x equal -2, now this is a little esoteric here, but it's still true. At x is equal to -2, you have a hole in the graph. So when you have a common factor like that, x plus 2 over x plus 2, you know x can't equal -2 because that will give you a denominator here. It's not going to be a vertical asymptote, it's going to be a hole in the graph right there. Okay? That's what, that would be the only other thing you had to do. That's way beyond what we're supposed to be doing now, but we did it anyway. Let me just quickly, show you what they did. They had degree of the numerator is equal to degree of the denominator, so that for the ratio of the leading coefficients is, leading terms is y is equal to 2. Exactly what we got. Horizontal asymptote. Vertical asymptote is where the denominator is equal to 0. That's x equal +1 or -1. which we got here. Okay, so those are your two vertical asymptotes. On the got it. Okay. Okay, they did other things, two real solutions. They actually are plotting the graph. We didn't. Remind me, next time we'll come back and plot the graph. They didn't say plot it, but they're doing it anyway. So that is on page, that's example. Same thing happened to me last time I taught this. Okay, we'll just start with the graph there. Got it? Thank you. All right, and the rest of you, have a great Thanksgiving.
Are you going to be here at 12 today?
At 12?
12:30, whatever. I get out of class at 12:15.
At what?
12:15, I get out of class.
Okay. I get out of class at 12:15 too,
Okay.
which means I'll either still be up here
In your office.
or I'll be in the office.
Okay.
Right at 12:15, I'll be up here.
I forgot to finish that test.
Okay.
I have like 2 left.
Right.
And I left blank. I forgot. I'm going to try to come and finish them, but they're really hard, but I'm not going to know how to do them. But I'm going to try to figure them out.
Okay, good.
But I'm pretty sure I can come today. I'm not sure. My dad calls me and tells me I have to come home.
Okay.
It's my little brother, so
Okay.
I'll let you know.
All righty.
Thank you.
Yeah, I'll either be up here or down in my office. All right. The rest of the class got out before I said this, but let me say it to everybody. Homework exercises include any of the either 5 or 7 or both, any of the odds 9 through 15. Okay? And then we'll do the rest of those next time. Have a great Thanksgiving.